All right. Good morning and welcome back to the lecture. Today is the last day we talk about data mining. So the plan is to wrap up this topic, and at the end of the lecture, if we have time, I'm going to talk about something not related to the course, but very important. All right, the slides that I'm going to use today are again mostly from Stanford. The problem that we want to look at today is clustering data into clusters or groups, okay? So the problem is defined as, okay, we have a set of points, okay? And with some notion of distance between these points, we want to group the points into some clusters, okay? With that have two properties. So members of a cluster are close or similar to each other, right? And members of different clusters are not similar to each other. In terms of type of problems we look at, the points that we are talking about are typically in high dimensional space. I'm going to talk more about it. And the similarity metric that we use is the Euclidean distance, cosine distance, Jacquard distance, or editing distance. Okay, here's a visualization of what we want to talk about today. We are given a bunch of points. This is in two-dimensional space, okay? And as soon as we look at these points, we realize that, or we identify groups, right? So, okay, a bunch of points are over there, a bunch of points are over there, right? So we can easily identify them, or our brain is really good at seeing these groups of points, right? And obviously there might be some outliers that don't seem to belong to any cluster. Okay, so that's basically what we want to do. But why do I talk about this in this course? Well, there are cases where we have many data points. Okay, and then as we said, each point is not in 2D, but rather in high dimensional space. So we are dealing with a lot of data. I'm getting some feedback. I'm going to mute everyone. So unmute yourself later when you want to talk. Okay, so is this really a difficult problem? It looks easy. As soon as we look at one of these images, we can immediately identify cluster of points. Yep, everything is pretty easy in two-dimensional space, right? And when we have small amount of data. And you're right, as soon as you look at something in 2D, you can realize, identify something, and that's correct, right? You're not wrong, it's correct. But the issue is, it's not the case in higher dimensional space. And in reality, in many problems, as I will present some examples next, you will see that we are dealing with tens or thousands, or even sometimes millions of dimensions. What's the problem with high dimensional space? The issue is that everything looks different in high dimensional space. For example, when you're working with like a space that has like 100 dimensions, when you look at every pairs of points, you realize that the distance is far, and it doesn't matter what pair of points you pick, the distance seems to be similar or the same, almost the same, right? So there are a bunch of problems that happen when we move to high dimensional space. There's a terminology for it. It's called the curse of dimensionality, if you want to look it up, if you're interested. There are a bunch of problems that rises when we go to these higher dimensions. So it's interesting. Let me present a few problems to motivate it. So in many experiments, we measure something, right? And then we want to basically see if what we measured can be classified into different clusters, right? So an example of that is this one, that there was an experiment where we measured 2 billion sky objects, right? So different things, the skies, stars, galaxies, quasars. And the task is to basically cluster them, okay? And we have 7 dimensions because we had like a measurement in 7 different frequencies. Okay, so for every point, every measurement is basically a set of 7 numbers, basically. And now I want to mention something here. Clustering is an unsupervised machine learning technique. In the previous lectures, we talked about supervised machine learning, and the word supervised comes from the fact that our input training data set must be labeled, right? So we had objects, we had labels, right? So training a model was basically trying to find a relationship between the data and the label so that we can label unseen data, right? That's why it's called supervised. Now, clustering is unsupervised, meaning that we're just given a bunch of data points, like here, without any labels, okay? And then we want to cluster them. We just say that, hey, these measurements look alike, right? They are similar. I don't know what they are, right? But I think they belong to the same group. And then here's another group of measurements, right? I think these photos or these measurements of the sky objects, they also look the same, right? So they cluster them into groups without any labels, really, okay? Obviously, people can do another step and look at them and say, hey, yes, like all of these objects in this group, or most of them belong to galaxies, for example. Someone can actually label them later to figure out what they are, but the job of clustering is not to label anything, but just to identify clusters of similar objects, okay? So in this problem, we had 7 dimensions, but we have a lot of data points, 2 billion data points. Let me give you another example. Okay, music CDs. I don't know. I think people at the Stanford still use CDs. I need to update this slide. I'm sorry. So, by the way, in the chat, let me know what you guys use these days to listen to music. Probably streaming, right? So let me know so that I update the slides. So. So we have a bunch of music CDs, and we want to actually cluster them into categories or groups. So we can represent a CD by a set of customers who bought it. Okay, and then similar CDs have similar sets of customers, right? So the thing is that if you can say these CDs look the same, right? And now if I buy one or a few CDs in that category, a recommender system can recommend other CDs in that category to me because it looks like I like that type of music, right? So we can build recommender systems using this. All right. I keep losing, okay. Is this a problem in high dimensional space? Yes, very, because how can we represent a CD? We can represent a CD by, as we said, the set of customers who bought that CD, right? Get my laser pointer here. All right. So a CD representation will look something like this. It looks like a binary vector, right? Or set, where here X1 is like customer 1, this is customer 2, customer 3, all the way to customer K. And this binary vector tells me if this customer bought the CD, right? So if it's 1, it means that customer 1 bought the CD. This one is 0, it means that customer 2 did not buy this CD, right? So we can imagine this to be a vector. And now the question is how big this vector is. And it can be very big. It depends. If it's on Amazon, for example, where we have millions of customers, then this vector can have millions or hundreds of millions of bits in it, right? And because that's how you represent your data point That's how many dimensions you have, right? From x1 to xk, so you have k dimensions, right? So that's crazy. You didn't tell me what you used to listen to music. Come on, people, give me some hints in the chat. So now moving on to documents, that's typically what we work with. We can also represent documents by a similar vector, right? Again, x1 to xk. Here, each dimension means, does a particular word appear in a document, right? This is again back to the bag of word idea, right? So x1, if we just sort all of the words that we have in the target language, right? This says, does word 1 appear in this document? Does word 2 appear in this document, right? So on and so forth. So how many dimensions we have? It will be the number of words you have in that language. So again, crazy high dimensional space, right? And then the idea is basically, what do we mean by clustering documents? The idea here is that documents with similar sets of words are probably talking about the same topic, right? That makes sense. So for example, we have a group of documents here. They look similar because they share so many words, right? So they might be talking about the same thing. All of them are talking about the University of Waterloo, for example, right? So it's good for clustering documents based on their topic. I mentioned a few times that like things that look similar, right? So we have to quantify the distance between objects, right? So I have two documents. What do you mean they're similar, not similar? I have two CDs, right? So what do you mean? What's the distance? So we have different choices, actually, specifically for documents, because we can represent them as a set of words or shingles, right, that we learned last time. So there are sets, right? So there are different ways to measure similarity. The obvious one is, because it's already sets, we can use Jacquard distance, right? Because that we learned that last time. That's a metric for finding the distance between two sets, right? We can also look at this set as a vector, right? Because it's a vector in high dimensional space, right? With k dimensions. So we can use something like cosine distance. Or similarly, just as points, right? I am in k dimensional space. This is a point in data space. There's another point in data space. And I can use Euclidean distance to find it, right? That's the line, basically, the straight line between those 2 points in that high dimensional space, right? Okay, Spotify, mostly streaming, YouTube, same, yeah, that's what I guessed. Cool. Should update the slide to Spotify. Now, what methods do we have for clustering? Let's be more specific about what we are talking about. At a high level, we can divide clustering techniques into two categories. So agglomerative techniques, or bottom-up, or divisive or top-down approach. In this lecture, we focus mostly on bottom-up approach. The bottom-up approach is simple. So you have n points, right? So at the beginning, we consider every point a cluster of its own. Okay, so we have n clusters. And then we try to merge nearby clusters into each other to basically have fewer number of clusters. Okay, so that's the idea. You can go all the way to one cluster. So the divisive or top-down approach, you start from one big cluster that contains all of the data points, and then you try to break it or split it into smaller clusters. And then again, you can go all the way to every point being a cluster of its own. here you might have a question, when do we stop? I need to talk about that. So, but that will happen later. So point assignment. So when we work with this problem, we typically need to keep track of two things. So we need to keep track of what clusters we have, right? And then also the membership information. So we have to know for every point which cluster it belongs to, right? So we need to keep track of this information. So the hierarchical clustering, or bottom-up approach, so it repeatedly combines two nearest clusters, okay? It looks pretty simple, but we have to be specific and define a few things, right? So when I say combine nearest clusters, right, there are some questions here. How do you represent a cluster of more than 1 point? So I'll give you an example here. So let's talk about 2D space. So this page is like a 2D space. So I have 1 point here, right? So I have coordinate. I can represent it, right? It has X and Y. Sorry for my bad handwriting, right? So that's 1 point. And I have another point, right? That one also has some X, Y coordinates, right? So I know how to represent points, right? But now if I tell you these 2 points are a cluster, how do I represent a cluster? How do I keep track of this cluster in my program? And then the second question is, you are saying combine nearest clusters. Okay, so suppose that I have another cluster here, and then I have another cluster over here. Right? What do you need? What do you mean by nearest? What do you mean? What is that? It's not a point, right? It's a set of points. Okay. So yes, so someone said, yes, it's the mean of the cluster, the average. That's one of the ideas that we can use. Exactly. So, and the last question is, when do you stop? Because this technique says repeatedly combine nearest clusters. If I keep doing that, everything will be one gigantic cluster, which is probably not good, right? So we need to answer that question as well. So, okay, so the first problem, how do you represent a cluster of many points? Okay, as was suggested, we can use the centroid, which is the average of the data points. So again, if I have, for example, a cluster of 3 points like this, right? In Euclidean space, we can calculate the average, right? And it would be a point probably around here. It's also probably the same idea as the center of gravity, right? So it will be a point here, and then it's called centroid, okay? And then this centroid, because it's a point in this Euclidean space, it has some X and Y coordinates, right? So I can keep track of my cluster by keeping track of the centroid of that cluster, right? So that's how I represent it, okay? So that's the answer to the first question. And also, as suggested in the chat, we can use some other techniques as well, right? So it's really an application dependent kind of thing. But average is probably the most common technique when we are working with Euclidean space. How to determine nearness of clusters? Okay, now I think we can answer this question, right? Because we have a centroid, and now we have another cluster over here, right, with some data points, and then it has a centroid like this, so we can define the distance. Oops, that was bad. From the centroid in one cluster to the centroid in the other cluster. So that would be the distance between clusters, right? That's now everything makes sense. So let's have a look at an example. Okay, so suppose that I have these 6 points. Okay, in different colors. Ignore colors for now. So, and we said in the bottom-up approach, every point is a cluster. Okay, so right now I have 6 clusters, right? Each has only 1 point. Totally fine, right? That's how I cluster. Now, how does hierarchical clustering works? combine nearest clusters. Okay, so out of all pairs of points, which ones are closer? These ones. So you can put them, so you merge them into one cluster. Okay, now we have 5 clusters, right? So 4 of them have 1 point and 1 of them has 2 points, right? And as we said, we can represent that by the centroid, which is the average, right? And it's literally, they are like 1, 2, right? So it's 1.5, and also for the y, same thing, right? So it's the average, right? Now that's one step. We can go to the next step, right? With the difference that instead of 6 clusters, now we have 5, right? And the way we should calculate distance is now we should consider the centroid, right? So forget about those 2 blue points. Just imagine there's 1 point, right, at where the x is. Now, which clusters are closer? Now here, for example, the green ones, we calculate the centroid, right? And then in the next step, which ones are closer? The blue and red ones. So we combine them and create a bigger cluster, and we calculate the centroid again. So the centroid of these 3 points will be again the average of those 3 points, right? So the x is 1 plus 2 plus 0 divided by 3, 1, right? So it's the mathematical average. And so on and so forth. So you can keep combining these clusters. Now, we also showed us the dendrogram here. Okay, so in the top, in the bottom right. So it actually shows how we combine the stuffs, right? So it shows that first we combine the blue ones, right? And the height of these lines indicate how far we had to go in order to merge, right? So the lowest line is the first merge, and then this one, the green ones, is the second merge, and then the merge of blue ones and the red ones was the next one. So the height of the lines indicate how far we had to go to combine the stuffs, and it can be used to determine when we can stop. Okay, it's one of the techniques. For example, we say there's a threshold, right? So if you have to go more than this distance to measure stuff, you should stop, because you are adding, like, things are too far to your clusters. Okay, so you can have like a cutoff threshold somewhere. Say if I reach that level, I stop. But there are other techniques, and we will talk about them. So what I want you to remember here is hierarchical clustering, starting from the cluster, single clusters, and then we merge them, right? And then you have to figure out when to stop. Is there any question before I move on? Everybody's happy? All right, so we also can talk about non-Euclidean space. What is non-Euclidean space? So Euclidean space, you know it, right? So it's basically, it's a continuous space. Points, every point makes sense, right? The concept of between points makes sense. The average makes sense, right? But non-Euclidean case is not like that. So non-Euclidean case is, for example, when my data points are something like this. A, B, C, and then I have another point that's represented as A, D, C, and then I have another one like this, right? So if my data points are like letters, right, set of letters, it's not Euclidean space, right? What does it mean? For example, here, can you calculate the centroid? No, average makes no sense, right? Basically, there's empty space between data points, right? So the space is only defined at our data points, right? There's nothing in between them. So average doesn't make sense. So we need to come up with other techniques, okay? We cannot calculate the centroid because average doesn't make any sense. So we use a different technique here. And and we pick a clustroid instead of centroid. What is a clustroid? So it's very similar concept to centroid, except that instead of a new point, which is the average of those points, it's one of the existing points, which has some property. For example, it is the closest one to the other points with some definition of closest, right? Because it's not Euclidean space, so you cannot just find the distance between the points in the way that we used to, right? With the straight line that connects the 2 points. We need different techniques. For example, the editing distance can be used to find how far the data points are from each other. So editing distance, for example, the editing distance of ABC and ADC is 1. It means how many changes you have to make in order to go from one word or sequence of letters to another sequence of letters. In this case, I only need to change B to D, right? To go from ABC to ADC. So the editing distance is 1, right? But ABC to book, more, right? How many? 4, 3, 4? I don't remember how it's defined exactly. So more changes, right? So that's how you define distance. And you can figure out a point that's closest to other points. And then how do you determine the nearness of clusters? It's the same as before, right? So you have a clustroid now for every cluster, and you can measure its distance to another clustroid in another cluster. So here's an example here. So we have 3 data points, okay? In Euclidean space, the whole space is defined, right? So you can take the average, and for example, the blue X is the centroid, right? In non-Euclidean space, the space between points are not defined, okay? So you cannot, and average doesn't make sense. So you have to pick one of the existing points, like for example, this one, because it's closer or closest to other data points with some definition of closest, right? How can you define it? For example, it can be the smallest maximum distance to other points, right? So for example, here it has the smallest maximum distance. So this one has this is the maximum distance, right? Between these 2 distances, this one is the maximum distance, right? So compared to this point, which has a maximum distance here from here to here, which is bigger, right? So this one has a smaller maximum distance, so we can pick that one. Or it can be the smallest average distance to other point, or it can be the smallest sum of the squares of distances to each other point, so to other points. So it's really application dependent, and you have to see which one makes more sense for that application, right? But these are different approaches that we can take. The important thing is that we pick one of the existing points, right? Because the space outside those points are not defined. Any questions? What I explained up to now is one approach, right, for measuring the distance between two clusters, right? We talked about Euclidean space and non-Euclidean space, but the idea was the same. So we pick a representative, right? It can be a centroid or a clustroid, and then we measure the distance between the representatives in each cluster, right? So that would be the distance between them. But now I'm going to talk about 2 other approaches that don't do this, right? They do this basically directly without picking a centroid or clustroid. So in some sense, they're, I think, easier. So the second approach says the minimum of the distances between any 2 points is the distance between 2 clusters. So it says if I have one cluster here and then another cluster here, right? So one cluster here, one cluster here. In our previous technique, what we had to do was to pick centroids, right? And then measure the distance between the centroids. Second approach says you don't need that. So you can just measure the intercluster distance, which is the minimum of the distance between any 2 points across the 2 clusters. So these 2 points are the closest ones across the clusters, right? So this is the distance between clusters. That's the second approach. It's simpler, right? The third approach is also interesting. So I draw it here. So again, so if the same roughly the same points. It really doesn't matter. Now it says you have two clusters, right? You want to measure the distance between the clusters. You want to quantify it. So it says, assume that you have merged them into one big cluster. Okay? And then come up with a metric for that cluster. And that can be the distance between those two previous clusters. For example, the distance between the farthest points, right? In that new big cluster, right? Forget about the small cluster. Think about the big cluster. So what's the biggest distance between the points in this new cluster? You can define that as the distance between the two clusters. And you can imagine that you can use different techniques for that, right? For example, as I said, you can use the diameter of the new cluster, which is the maximum distance between points in the new cluster, or the average distance between the points. Also, we have the density-based approaches that actually divides the average by the number of data points, right? Because it's kind of unfair if you ignore the number of data points, right? Because as we increase the number of data points, it's possible that this one point is a little bit far from other ones, and then that will change the diameter of the cluster significantly, right? So in some applications, it makes sense to normalize it by the number of data points we have in the cluster, right? These are density-based approaches. They, for example, calculate the average distance between points in the new cluster and divide it by the number of data points, and that will be the distance between the two original clusters. All right, enough of defining and figuring out how to measure the distance. Okay, how can we actually cluster? So suppose that we use one of these techniques that I talked about. Okay, it doesn't matter. The naive approach is, unfortunately, is O of n cubed for clustering. How? In every step, you need to basically consider all pairs of clusters, right? So which is an order of n, the number of data points that you have. So you need two loops for that, right? To find all of the pairs in a cluster, right? And then you measure the distance between those clusters. And then you need another pass to find which one is the closest one, right? Which two are the closest one, so that you can merge them, right? So the naive approach is O of n cubed, which is terrible, right? If you come up with an n cubed solution in an interview, you probably don't get that job. Obviously, there are a little bit better ways of implementing it. You can reduce it to O of n squared log n. It's still very bad. Even log n is, even n squared is not good, especially for big data. There's no way we can handle n squared, right? So we need another approach, right? We cannot just do some naive searching or finding the nearest clusters. That doesn't work. And hence, we have techniques for big data, right? To be able to cluster efficiently. And the most famous technique probably is Kmeans. Kmeans clustering. I'm going to explain it here. So let's see what we have done until now. So, okay, we talked about clusters, talked about techniques for measuring distance between clusters, right? And then we realized that a naive approach won't work. So we need a smarter approach, right, for big data. So that's what has happened until now. And now we want to talk about this new algorithm. So assume we're Euclidean space for now. And the thing about this algorithm is that we start by picking k, the number of clusters. K in K-means is coming from the number of clusters, okay? And here the assumption is that we know how many clusters we have, okay? Or how many clusters we want to find. So for now, let's suppose that we know that. So suppose that that information is kind of provided, okay? At the end, I will talk about how to find what is a good k to use, okay? But for now, we know how many. For example, we are told 2 clusters, 5 clusters, okay? How does this algorithm work? So I have 2 slides that explains it, but let me explain it using the figure that I have here. So I have some data points, okay? And k is 2, okay? I'm told somehow that the best value for k is 2. So my job is to basically find two clusters using the K-means algorithm. How does it work? It's actually pretty simple and neat. First, it says pick one point randomly. That will be your first cluster, okay? And then pick the rest of the points. So we have to pick K, right? Pick the rest of K minus 1 points as far as possible from the previous points. This is an important trick in this algorithm. This is to make sure the clusters are different from one another as much as possible. So for example, in this case, what is the farthest point? So if I want to pick, so remember again, I back up. You pick the first point randomly, which happens to be the blue one, for example. And then the rest of them will be as far as possible. In this case, K is 2, so I need to pick one more. The farthest one will be the one in far left, right? So this is the initialization phase of this algorithm. So we pick a random one and then the next ones as far as possible, okay? Now, to wrap up the first round, what we do, okay, so we have two clusters right now, the blue one and the pink one, but there are so many points that we haven't studied yet, right? So it's simple. Based on those clusters, you see which cluster the remaining points belong to. Very simple, right? So you say that, okay, all of these points are closer to the blue cluster than the pink cluster, right? And then these ones belong to the red or pink cluster, okay? So that's the end of the first round. Now, so this is an iterative algorithm, okay? So we need to go to other rounds, and it's very simple. There's a question I'll answer, and then we move on. Okay. Can the two K minus 1 farthest points from blue point be next to each other? No. So every time you pick, so if for example, if K was 3, right? It doesn't really make sense for these data points, so it won't look good, but it will be the farthest from the previous selected ones, right? So if K is 3 and I need to pick another cluster, I don't know, the farthest point from those two, not just the blue one, from both of them is probably here, I think, okay? So it can't be here, right? It's not just from the blue one, but from the previous ones. That was a very good question. So as far as possible from the other one. So we want, and you will get the idea when you learn the algorithm completely, you realize that, oh, okay, it makes sense that they should be far from each other, because otherwise the algorithm won't work, okay? Because these points are supposed to be kind of the starting point of that clusters, and if you pick them right beside one another, the algorithm won't work, okay? That was a good question. So okay, this is the end of this round. We are done. So we pick some clusters and we assign points to them, okay? Now, we go to the next round, right? At the start of the first round, my centroid was that point because it only had one point, right? So it was its own centroid, right? But now that we added some other points, the centroid may not be that point anymore, right? For example, when we go to the second round and we calculate the centroid for each cluster, you realize that, oh, the centroid actually moves, right? To there and there for blue and pink cluster, right? So, okay, now we are in the second round. We have updated the centroid, but you may say, wait a second, based on this new cluster, based on the new centroids that you have calculated, the membership can change, right? Because, for example, this point here now is closer to the new centroid in the pink cluster rather than the blue cluster. Previously, it was not the case, but now the centroids have moved, and now the membership should change. Sure, so you should do that. So you should recalculate the membership. For every point, figure out which centroid it is closest to. And if There is a change, update that. That's the end of round 2. The rest of the rounds are exactly the same. So what happens is that at the beginning of every round, we update the centroid, and because the centroid moves, the membership may change, right? So we update that again, that causes the centroid to change, so on and so forth. So we repeat this process until it stabilizes. You will reach a state that known points move between clusters, and because your clusters don't change, their centroid won't change as a result. Therefore, we have converged, right? It won't change anymore. So in this case, if we want to follow and move on to the third round, you see that, okay, I changed one point to belong to the pin cluster. Now the centroid will change, and I'm exaggerating here a little bit so that it's easier to see the change. So the centroids have changed. Now, again, the membership will change. So we continue doing this until there's no change, right? We arrive at the state, for example, like this, that no points change, so the centroid won't change and the membership won't change. So we converge. That's the end of these iterations. So we can see it's a very, very simple algorithm. So won't we reach the same result if we pick 2 points randomly? Okay, so that's a good question, right? It's if you pick the points randomly, do we converge to the same results? Not necessarily. Not necessarily. Like, for example, I'm not 100% sure. I have to think about this, okay? But if we start from these 2 points, like I choose randomly, right? And those 2 points are selected. The issue with that is it may not, the case might be that it may converge to the same one, but it may not converge to the same one, right? So not necessarily. You can see that, especially if the clusteroids are very close to one another, it's possible that it chooses some suboptimal case at the end, right? Because they're so close, I think this one cannot grow, probably. So we will be in trouble. Or there are some cases, more sophisticated cases, that it causes problems. So the idea, the intuition behind it is that, for example, if you have like a cluster of points here, a cluster of points here, and cluster of points around here, this idea of the farthest point is like this. Okay, we pick a centroid or a point randomly, let's say here, right? And then we say, pick another one as far as possible, so it won't be inside the same cluster, but rather in one of those. So we say, okay, here, for example, and then we say, okay, now the next one as far, it should be in this one. So that's the idea, right? So if k is the correct number, and then we really have clusters, when we pick them as far as possible, right? We start from a more reasonable location, and we can have better cluster rather than all points being here, right? It's not clear what will happen if that's the case. Okay, those were good questions. So that's K-means. Any questions about K-means? There's one more. How do we pick K? So let's talk about that as well. So there are different approaches. One approach is trial and error, basically. So you try different values of K, and you look at the average distance to centroid in your clusters. Okay, what does that mean? So if K is 1, it means that everything is in one big cluster. So the average distance to centroid will be very high here, right? And then you increase K to 2, say, okay, now find 2 clusters. Probably the average distance drops significantly, right? Because there will be a better fit to the data, right? And then the behavior that you will see is like this. As you increase K, the average distance to centroid falls rapidly up to a value of k. And then after that, it decreases, but very slowly, right? It will decrease, right? Because, for example, if I have n points, I can go all the way to k equals n, where every point is its own centroid, and the average distance to centroid in that case will be 0, right? So it goes to 0, but the behavior is interesting because at the beginning it falls very rapidly, but then it slows down. The point at which this behavior changes is the best value of k. This is also called the elbow point because this shape is like an arm, right? So if this is the hand, my drawing is excellent, right? It's like an arm, right? And that's the elbow point, right? That's the best value of k. Let me give you an example. So here, k equals 2 for these data points, right? And you know visually the best k is 3, right? So if we pick a k that's too few, something like this happens, that the centroid will be far from the data points, right? Because you're forcing 2 clusters or more clusters into one, right? So the average distance will be big. And then you increase k, then you see it rapidly drops to a lower value, right? The average distance is now much lower compared to the previous case. And then you can see that if you continue forcing higher number of clusters, it doesn't improve that much, right? So that will be, so the previous one should be the elbow point, and the best value is 3. That's about how to pick k. Any questions? The last thing that remains is the explanation of how to implement this in MapReduce. Good question. How do we remove outliers? One possibility is, for example, here, if you go back, right? So we can see that the outliers are causing some problems for us, right? It made those clusters much bigger in terms of distance from centroid, right? Than what they really need to be, right? So one possibility is that, well, you figure out k is, okay, the best one is 3, and you figure out your clusters, then you can inspect your points, right? And then you see that, look, there are some points that are very different from the rest of the points in those clusters. So, for example, if this is my, like, suppose that, like, here, right? This is my centroid, for example, right? And you see that, look, all of the points, like this is like the maximum distance pretty much to it. And then all of a sudden there's a point that's much farther from the centroid, right? So you can, one way to get rid of outlier, to consider that as an outlier, right? And remove those points. Say that, look, this, if I look at the distribution of distances to the centroid, everything is pretty reasonable, and then all of a sudden there is some that are very far from the centroid, so we can eliminate those. If you don't have many outliers, they won't impact the algorithm, right? Because they should, in order to impact the algorithm, you should move the centroid a lot, right, to mess with the algorithm. But the thing is, for example, if I have tens or hundreds of points or even thousands of points in a cluster, and then I have an outlier over here, it cannot move the center of gravity that much, right? Because it's an average, like there are 1,000 points there and 1 point, so that 1 point cannot move the centroid that much. So it doesn't mess with the algorithm. So we can safely run Kmeans, I think, and then you remove some points if you want, right? All right, good question. So let's move on to the MapReduce implementation. It's actually pretty straightforward. So let me draw some points here again to explain the algorithm. And then maybe some points over here. I'm drawing few points, right? You can imagine we have more points. So basically, my point is like 3 clusters probably, okay? So what we do in the mapper class, in the setup phase, we load some side data. And the side data that we are loading here is the cluster information, right? So in Kmeans, if we assume that K is 3, what do you mean by loading cluster information? What information is that? It's basically your centroids, right? So it's like 3 points, basically. So for example, here's my current centroid, here's my current centroid, and then here's my current centroid, right? So call them C1, C2, sorry for bad handwriting, C3, okay? So basically loading cluster data is basically loading C1, C2, C3. Right? So it's not a lot of data, so it's totally safe to load them as side data. It's not the input of the map, but rather some side data we are loading, right? The actual data that we load are these points, right? So these points are the input trace that the mapper consumes. So let's see what map does. So the map, in every call to the map function, we process one of the data points, okay? Not the centroids, but rather points like this guy, okay? So what do we do? It says emit this thing. Okay, so let's see what it emits. So it emits key value pair. What is the key? It says clusters dot, so this data structure that we loaded, dot find nearest. Okay, so that data structure also has a method called find nearest, and that accepts a vector, which is a data point, and it tells you which cluster it belongs to, okay? Just finds, it measures the distance to all of these centroids and tells you, okay, it's closer to this one, right? So in this case, if I'm processing this point and I call the function, what does it return? It probably returns C3, right? That's the nearest centroid, right? And so it emits C3 and what? The vector, the point itself, right? So this one, let's call this one P1, right? Point 1, right? So it emits C3 and P1. Makes sense? And we process all of the data points like this. So for every point, we emit the centroid that, or the cluster that it's closest to, and the point itself. Okay? So we do the same thing. For example, here P2, right? Same thing, right? So it's closer to C3. So we emit, for example, C3 and P2, right? And for another point that's here, for example, this is P5, for instance. This one is, so for that one, we should emit C1 and P5. Makes sense? Now, what happens in the reducer? The reducer will get a cluster ID, right? So these things, right? Grouped by the values, right? So for example, a reducer can receive something like C3 and a set of points, right? That were closer to it, right? Like this one, for example, P1, right? P2. And then, for example, this, let's say this guy here is like P6, right? So it will get P6 as well. Make sense? So it gets this thing, the key, right? And the values. And the values were the points that were determined to be closer to that centroid, right? And now, what do we need to do in K-means? So we have determined, okay, so the points belong to this centroid based on the new centroids. And now all we have to do is to update our centroid, right? So very simple. We basically take the average of these points. Very simple. That's what we are doing here, right? And then what do we emit? We emit something like C3, right? And sum and count. So for example, the new centroid will be here, right? So this one has some coordinates, so we put it here, right? That would be the average, and we emit that. And then this is one round. So in the next round, we basically load this data as side data again, and the algorithm continues. Right? So we do the same thing for C1 and C2 as well. So we write it, and then we read it again. and then we process the points again and we iterate. Questions? We got one in the chat, so let me read that. So to find the right k, we need to run the whole algorithm for every possible choice of k. It sounds costly. Yes, it is. If k is a small, it's not too bad, right? So it's 3 or 4, so we need to run it 3 or 4 times. Okay, not too bad. If k is bigger, it becomes more problematic. So that's one possibility, right? It works in some cases pretty nicely. But there are other techniques if you think this is bad for some applications. So there are other techniques you can use. The other approach that you can use is this. So I have a lot of data, right? And then, so that naive approach doesn't work. That's like O of n cubed, right? This is stupid. So what I can do is I can downsample my data, right? And if you uniformly downsample your data, there's a very high chance that you end up with some points in every cluster, right? Because you're just getting rid of points randomly, so every cluster will have fewer and fewer points, but hopefully you don't destroy anything, right? So you don't destroy a cluster, meaning that you don't remove all of the points from a cluster. So if you randomly downsample, you most probably preserve the clusters, but it will be a downscale version of your entire data, right? And then when you get that downsample version, you can run the naive approach, the n cubed one, right? It's terrible performance, but because the data, you don't have many data points, it finishes in reasonable amount of time, right? And that one is a brute force technique. So it tells you, it will tell you what is the best k. So that's another way to do this. So there are different approaches. Make sense? Other questions? So I wait another moment to see if there's any questions. There's another important thing I want to talk about for a few minutes. Questions about Kmeans? All right. The thing I want to talk about is not related to this course, but is very important. I typically try to talk about this every time I teach this class. And it is this thing. Can someone tell me what it means? The first time I saw it, I think I read it. Please go ahead.
Sorry, I was just going to ask if it means like the idea that getting a job in Silicon Valley is the end all be all.
Yeah. So it's for California, right? But it really considers or includes all of the big tech companies, not necessarily in California. So it's a trend, right? Very serious amongst CS students, especially. And the thinking is you either get a job at one of these big tech companies or bust, right? You are screwed if you don't. So so I want to talk about it a little bit. It came up. I realized that it's a serious issue. I was working on a survey. It was a climate survey I was working on. I was designing the survey to figure out how is the university life, how the university life is for you guys. And it's part of my job in one of the committees I'm in. And I ran as pilot, and I was surprised that so many students talk about the stress and pressure that this causes, right? And I was surprised. I didn't know that it's so serious. So I thought I spent a few minutes and I talk about this, and this is my point of view. I'm not giving you advice, it's just my view. So please hear me out. So I'm not arguing against this, okay? So just to make my point clear, it's totally fine, right? So big tech companies need great engineers, and that's you guys, okay? So no problem with that. It is great for some of you. That's my point, right? These companies are great. I have worked with them before. I didn't work for them, but I had projects with Google, for example, in the past. It's totally cool, right? But the issue is thinking that everybody must follow the same pattern. And these trends always exist. Even when I was doing my undergrad, there was a trend. It was a different trend, but there was a trend. There's always a trend, right? And unfortunately, it's repeated over and over and over again, and it becomes the goal without you think about this, right? You think, yep, so that should be it, right? Otherwise, I'm screwed, right? That is the standard. The issue is that is not the case for everybody. And I think the most problematic one is that, okay, if it's great for you, then you go get it, okay? No problem with that. The issue I have is that if it's not for you, there are two routes here. Either you get a job at one of these companies or you don't. If you get a job at one of these companies, after a few years, you will realize finally that it is not for you. And it will be a very sad day for you because you are successful and depressed. Think about this. The second route is you don't get a job at one of these companies and forever you think that you lost the game while you don't know that it wasn't really for you. So my point is think about all possible options that you have. It might be other companies, right? Living in California has positive and negative things, right? If you have done internship there, you know about it. If you haven't, you can ask people who live there, right? It has positive things, it has bad things. Like traffic, are you kidding me? I mean, I gave a talk at Google and my hotel was like 10-15 minutes away. And like during rush hour, it was close to an hour. Like, and just imagine that this is like everyday thing, right? It's not for me, right? That's like a simple example, or the cost of expense. And there's so many personal things that you have to think about. So other companies might be totally fine, right? Especially depending on your living styles. You may want to live somewhere that you want to buy a big house with a farm, right? You cannot do that near Google, right? The crappiest house starts above $1 million, right? So the salary is high, but expenses are also very high. So other companies also a great option. So you have to consider. And then I have two more. So startups, very important, right? Something that you might be afraid of, but you should think about it seriously, right? As you get older and older, it becomes much more difficult to do startups because you have life commitments, things like that, that makes it more risky for you. So if you love it, don't be afraid to do this. You may say, but what happens if it fails? I asked a bunch of people in business, and many people told me that a failed startup in your CV is a positive thing. Compared to someone who didn't have this experience, you went through this experience and you gained experience that other people don't have. And people understand that many startups fail, right? That's the nature of it. So if you have an idea, if you love this path, take it. Okay? We have great companies. Your job is like an investment, the biggest investment of your life. The same way when you buy stocks, you think about future, right? You buy something because you think the price will go up, right? So if you start a job in a company, you should also think about the future of that company, right? Is the picture going to remain the same in 10 to 20 years from now? So if you wake up tomorrow, 20 years from now, I ask you, what are the big tech companies? Do you think it will be the same names that we see today? I bet not, right? And some of those are coming from startups that are being built today, right? And again, it can be you. We have great companies, but someone should kick their asses, and it can be you with a great startup. And finally, another possibility is grad school, right? Again, this can be also a trend. I am originally from the Middle East, and I know that in Asia, in like India, China, and in Middle East, families just want you to get a high degree in whatever, right? So that's also a trend, right? That was the trend that I was in when I was an undergrad. I'm really lucky that it worked out for me. This is what I really love. But it's not the case for many people, right? I didn't have this vision back then. I followed the trend. I was really lucky that it worked out for me at the end of the day. But grad school, if you really like, with open eyes, if you want to become a scientist, take this path. We need great scientists, right? Unfortunately, our education system does not tell us that we suck at science, right? We always think that science is this great thing that we can learn maybe 1% of it. It is not true. There are very big fundamental questions in science that are still remained unanswered. And as we discover more and more, we realize we don't know anything. So we need great scientists. And if that is something you love, grad school is a great path for you. Okay, I can talk about science a lot, and I would love to, but we don't have time. But give you two quick examples. COVID-19 showed that we suck at science. After 2 years, we could not get rid of it. If this disease had a little bit, just a little bit higher fatality rate, our race could be wiped out. Right? Just imagine if more doctors and nurses lose their life to this disease. The whole system would fall apart, right? And the fatality rate of this disease was minimal, right? Lower than some regular flus, right? Still devastating. And we didn't have the science to stop it, right? Are like 2 or 3 years into it, and the vaccines are not very effective still, right? And we don't know still what will happen, right? That's one example. Moving forward, we don't have time. The second one, you may say, what are you talking about that we suck at science? We are going to go to Mars. Elon Musk wants to take us to Mars. Suppose that happens tomorrow. We have discovered 0% of our universe. My point is, yes, that's great. That's the edge of technology and science, right? But it's always good to have some perspective. The distance between Earth and Mars, right now, a very ambitious target for us, is 0 in our observable universe, and we cannot reach it. That's the problem. Right? So we need great scientists, and if that's who you are, grad school. My point is, there are many possibilities, and there are other possibilities other than what I listed. My point is, follow your dream and not a stupid trend, okay? Because it may not be for you, and you will be devastated in a few years, okay? So I want to wrap up by answering one question. You may say, but money is in these things, right? And my course is also included in this trend, big data, all of these hot topics, right? Do you really love it, or you follow the trend? You may say, but there's money in these things, right? These big companies in big data, right? And other hot topics. If that's your goal, right? If money is your goal, the best path is still to follow your dream. Let me wrap up by showing this photo. I don't think this guy went after money, or if he did, it was via the path of following his dream. Bill Gates and his friends started in a garage. I think they were following their dream, not money. I'm saying even if you want to have a lot of money, probably the best path is to follow your dream. And that is Jeff Bezos in his company back then, the richest guy, right? That's the end. Thanks. Now second richest, right? So I'm going to stop recording and I will be around a little bit more.